So I think we can start Gauss's law now. We are ready for it. So we already realized that the flux for this plus charge at a distance, let's say over here, we said that the flux was Q over epsilon 0. Did we? Yes? Yes, we did. Now, Gauss's law tells you that, so as you remember, I started with this, and now let me take any kind of a surface. And these lines now extend out to here. What do you think is the red phi e or the blue phi e? Let me just say blue one. For the blue surface, what do you think it is?
Same.
It is the same. Why?
Because the number of
Field line. Number of field lines are the same, right? And we said that flux is proportional to the number of field lines. So the flux is still Q over epsilon 0. But how can we describe the flux for the blue curve? We can describe it by closed integral E dot dA. Okay? And you can imagine that this is true if you put another charge here. So let's make that a thought experiment. So Q1 will create its own thing here, and it will have its own surface here, and it will have phi of 1, which is Q1 over epsilon 0. Let me say there is also Q2 here. It is also creating some flux, and its flux around some radius is going to be phi 2, which is Q2 over epsilon 0. Now, if I draw a blue surface which encompasses both of them, then the flux is simply going to be phi 1 plus phi 2, which means flux is going to be Q1 plus Q2 over epsilon 0. In other words, it's going to be Q enclosed over epsilon 0. Okay? So that leads us to, if you combine all this logical sequence, you arrive at the most general form of Gauss's law, and it tells you that closed surface integral of E dot dA is Q enclosed over epsilon 0. That's Gauss's law. Do you understand this? Yes? Okay, good. For example, let me give you an example. There is a Q here plus Q here, and I want to get the flux over here. What is the flux over there? Anyone? Okay, let me just do this. What is the flux over here? Q over epsilon 0, right? What is the flux over here? 0. Because? Exactly. So enclosed Q is 0, right? So this flux is going to be 0, while any kind of such surface will have a flux of Q over epsilon 0. Okay? Do you have any problem with this?
Can you repeat?
Yes, of course, of course. So this spherical surface, or it could be anything really, any kind of surface, closed surface over here, okay, the flux is 0 because it is enclosing no charge. But if it would enclose some part of the charge, then the flux would change. So for example, this surface has Q over epsilon 0. Okay? Thank you. Now let's show that Gauss equals Coulomb. Okay? Why is that? Because we can actually derive, so we derived the electric field at a distance from a charge plus Q. Let's say there's a plus Q here, and at some distance over here, let me call this R. At some distance, E would be 1 over 4 pi epsilon 0 Q over R squared, right? We know this from Coulomb. That's Coulomb. This is the Coulomb. But what do we know from Gauss's law? We know that flux is equal to Q over epsilon 0. And what is flux? Flux is integral E dot dA. I forgot to talk about this circle. Please don't be scared by that circle. It just means that the surface is closed. Okay? It's a closed surface. Otherwise, it's the regular integral. So what's the integral of E times dA? Since always it's perpendicular, right? This is perpendicular everywhere. So what's going to be E dot dA integral? E times A, right? E times A. What is A? 4 pi r squared. So what do we get from Coulomb's law? From Coulomb's law, we get Q over epsilon 0 is equal to E times 4 pi r squared. And hence, from Coulomb's law, we have derived, from Gauss's law, we know that this is the case, and hence, from Gauss's law, we have derived Coulomb's law. Do you see? I'm not sure about this, but I don't think Gauss ever worried about physics. Was he? Does anyone know Gauss? No? Closely, maybe you have read his autobiography or something. It's really a mathematical tool that he created, and that's why we call it Gauss's law. And that tool is converting volume integrals into surface integrals, and converting surface integrals into line integrals, and things like that. Okay? So that's what we are doing. We are converting volume integral into surface integral. Where is the volume integral? The volume integral is the volume integral of charge. So when you say Q enclosed, you are integrating over the whole volume and counting all the charges. So a volume integral equals to a surface integral. Okay, everybody's happy? Yes.
How do you understand E is perpendicular to the surface? Is it given? Or is it because it's...
Okay, very good question. So we assume that the charge is at the center of this surface. Okay? So charge is at the center, and the lines, the electric field lines are going straight out of the center. And when you go, so this is the sphere, this is the center, and it's going like this, so it must be 90 degrees. Is this enough explanation?
Because it's a sphere, or...
It is because it's a sphere, uno, and dos, it is because, that's my Spanish, that's where it ends, uno, dos. And second, because it is at the center.
Okay.
If it's not at the center, then the electric field lines are not perpendicular. Then Gauss's law becomes useless. It's still true. It's still true. Integral E dot dA is always Q enclosed over epsilon 0. But if you don't have symmetry, you remember the password? If you don't have the symmetry, then you can't find the electric field. Okay? All right. So let's talk about application of Gauss's law. Applications of Gauss's law. So, since it's important, I'm going to repeat it one more time. This is your formula. E dot dA equals Q enclosed over epsilon 0. Always valid, not always applied. Let me not say useful, not always applied. Applied when you have symmetries. So you have to find a surface, come up with a surface, Gauss surface, where electric field lines are either perpendicular or parallel. Okay? So in this particular case, when I have a charge right in the middle of a spherical surface, then all charges, all electric field lines are going perpendicular to the surface. But if I wrap it with a cylindrical surface, that's not the case, right? Do you understand this? This is very important. Okay. Now, let's look at an example where cylindrical surface would work. And our example is an old friend from once upon a time, a wire. Okay? But it has to go to infinity. Otherwise, you cannot apply Gauss's law if it doesn't go to infinity. Okay? So it goes to infinity. We already solved this. Do you remember? We had to take lots of integrals. Do you remember? Now we will almost not take an integral, and we will get the same result. That's the beauty of Gauss's law. So, why we can't do? Very good. Let's see why we can do, and then I will tell you why we can't do. Why we can do, because... So let me just start with this. If I take a spherical surface, is it a reasonable surface? No. Why? Because I know that electric field lines are going like this. right? Like if there's a, like they are going out like this, so they will be not crossing this one. Maybe at some particular points they will cross perpendicularly or in parallel, but not everywhere, right? So as these electric field lines suggest, we need to use a cylinder. So let's imagine a cylinder. And this is the height of the cylinder, this is the radius of the cylinder. Now we are happy. Why we are happy? Because why we are happy?
It's like we have a lot of disks. Yeah, we can integrate the.
Yes, yes. The electric field lines are going out of the surface perpendicularly. Even when they are not going perpendicularly, they are going parallel. So we are going to have zero contribution from here. Integral of E dot dA at the top will be 0. The same integral at the bottom will be 0. Do you understand this? Yes. Parallel right on top of this surface. Yalayıp geçiyor. It's tangent to that surface, right? It goes like this. Well,
But it is not parallel to the surface vector.
yes, it is perpendicular to the surface vector. Sorry if I misled you in that sense. It is perpendicular to the surface vector, but it is parallel to the surface, right? Because you remember surface vector is parallel to the surface, right? So, should I always talk about surface or surface vector? Which one do you prefer? Surface, right? Yes. So it's perpendicular to the surface on the sides. So that's where we are going to get our surface integral. The rest will contribute 0.
So it's like the wrapper paper.
Yeah, exactly, exactly. But the paper has top and bottom, but from top and bottom, we are not going to get any contribution. It has to be closed surface. Otherwise, the theorem doesn't work. Good. So our closed surface integral has only one term, and it comes from the sides, and it is E times, what's the area of the sides? 2 pi r h, right? 2 pi r is the length of the cylinder and h is the height. So 2 pi r h has to be equal to q over epsilon 0, right? So E is equal to q over 2 pi epsilon 0 h times r. Now, what can we call this one? Yes, I'm actually, I shouldn't be saying q. I should be already saying lambda times h here, because that's the amount of charge that is enclosed. Do you see? This is h. I'm enclosing only that portion of the wire, right? So that portion has a charge of lambda times h, right? So already there I get rid of q, and what is my result? Lambda over 2 pi epsilon 0 r. Do you remember this result from before? It came after we solved the hardest integral, and then we had to also take it to infinity, etc., right? But now especially if you are used to applying Gauss's law, it works like a charm. Now comes your question. Why it doesn't work when it's finite, right? When it's finite, you know that the electric field over here is like this, over here is like this, like has weird shape. Okay, so if you wrap it with a cylinder, then not all this will not be perpendicular, right? Maybe some of them are, but usually these angles are neither parallel nor perpendicular. So that's why you are not going to get easy integrals. You're not going to get just straight E times A. Yes.
Even the top of the cylinder is not going to be zero this time, right?
Yes, exactly. Exactly. Very good. Yes.
In the first time, I didn't understand actually it was on the top side why total flat is zero.
Yes, okay. So in here, this thing is infinite, okay? So since that is infinite, the electric field is always going outwards, okay? Perfectly straight, like perpendicular to the wire. And so you have a wire here. This is your surface, and the surface is perpendicular to the wire, right? And the fields are going out. They are all parallel to this surface.
It cannot go to the
Yes, it doesn't cross it. Okay?
How did you found on the in the up of the page?
Mm-hmm.
Can you go there? Lambda. How could you found lambda times h?
Very good question. So this cylinder has a height of h, right? And it's, let's say it starts from 0 cylinder and it goes up to h. So it's only covering a certain length of the wire, and that length is h. And length times the charge, linear charge density gives you Q enclosed charge. We are not enclosing the rest of the wire with this surface. Yes?
In that butterfly catcher.
Yes. Yes.
Could you find the electric field of that shape, something like that? It was too hard for us, so we left it like that.
Well, in Gauss's law, we never deal with butterfly catchers because it's not symmetrical. Very good. One, and DOS is it's not closed. Very good. Okay. So we are dealing with closed symmetric surfaces. Any other questions? Yes.
Then without writing lambda times h for q, we can find it later from
Q over h equals lambda. Yes. But I had to write Q enclosed, and I didn't write Q enclosed. Very good. All very good questions. Shows that you are following very carefully. Really happy. Okay, good. So lambda over 2 pi epsilon 0 r, and if we go back, we are going to find the same thing somewhere here, right? Lambda over 2 pi epsilon 0 r. Do you see? And we got it after the integral. Let's see if we can find the sigma over 2 epsilon 0. Okay? Let's see if we can do that. Ready? Okay. Let's do the infinite sheet. And just for the reason why the wire doesn't work, this also doesn't work when it's not infinite, right? So you have an infinite sheet. What kind of Gauss surface would you propose here to find the electric field? Circle.
Circle, so it's against cylinder.
Against cylinder.
But we are going to use the circular faces.
Yes. Can I have some weird shape like this also? Maybe?
I mean, if it is perpendicular, right?
Yes, exactly. If it's perpendicular, I can also have that. But let me not confuse you with this. Let me use cylinder. Okay. Again, I have a cylinder, and it doesn't matter, but the height is h, let's say. So it doesn't matter, so I will not even write it. What matters here is r. So r has its projection over here, right? So if this is sigma, what is Q enclosed? Sigma A, right? So sigma times pi r squared. That's what Q enclosed is, right? Now, how about the electric field? There is an electric field going out in this direction, which is E, and another one that is going out in this direction, which is also E. So what is the contribution to the total flux from the right-hand side? E times A. Everybody agrees with this? E times the area, right? Let me just write this as sigma times A as well. And flux left is E times A as well, because the area vector is pointing to the left here and to the right here. It's aligned with the electric field direction. So 2E times A's total flux is 2EA. You see how simple it is? Right? We started with a ring. We integrated the ring. Well, integrated, half integrated. Then we integrated to find the disk. Then we took the disk to infinity. But nothing like that. Just 2 times E times A should be equal to sigma times A over epsilon 0. So what is E? Sigma over 2 epsilon 0. That's it. Are you happy? I am happy too. Very good. Tell me.
So, if we have to take when time infinitely big, then how can Gauss' law have real life?
Very good question. So you can say that whenever the plate, the sizes of the plate is much larger than your distances, then you can simply use sigma over 2 epsilon 0. It's a very good approximation. It's just like assuming that the Earth is flat close by, but it's not, right? Do you see what I mean? Like,
We're so small and so
yeah, we are so small and the radius of Earth is so large. Right? Any other questions? It depends on your application, really. Okay.
In this example, we were looking for that chamber
Yes?
2D area, and
Yes.
then we drew the cylinder.
Yes. Yes. By the way, that reminds me that we forgot to talk about the sides. What happens to the sides? No, it's 0. Right? Because the electric field is parallel to the surface. Do you see? This time the electric field is parallel to the surface. Yes, what's your question?
Yes, I was trying to figure this.
Very good, very good.
It doesn't have a thickness, right?
Not because of that, but because what the cylinder doesn't have a thickness. Yes,
The plate.
the plane doesn't have a thickness, but that's
Otherwise, it will be.
no, it can have a thickness. Why that would be a problem?
Then we have perpendicular lines to the sides of the cylinder.
But it's infinite.
Yeah, sorry.
Yes? Okay. Yes.
Can we change the order of the cylinder?
No. Because if orientation, right?
Yes, orientation.
If you change the orientation, you will start getting flux from the sides. And that defeats the purpose. Your purpose is to make your life easy. So you are the one who is drawing the cylinder, not us, okay? So hence you want your life easy and you never draw a tilted cylinder. If you do draw a tilted cylinder, you can still calculate the integral. You will still get Q enclosed over epsilon 0. But that would be like not even this, but some acrobatic way of showing your ear. Yes.
Do Gauss surface need to be infinitely big? I mean, if we left with R in this equation, we say that it is very big, or Gauss surface just feel like small, infinitely.
Gauss's surface can be as small or as large as you want, provided that it serves your purpose. Okay? Size doesn't matter here. Any other question? No other questions. Okay, good. So let me talk about uniformly charged sphere. Now, uniformly charged sphere you can get confused whether it is like this and there is no charge inside, or whether it is like that, but all the charges are inside, uniformly distributed. You see what I mean? So, for this to happen, okay, I'm just doing something that is yeah. For this to happen, you have to have an insulator. And this one happens when you have a metal. So please read the questions very, very carefully. Let's say they say conducting sphere is uniformly charged. What they mean is it's uniformly charged on the surface. Okay? Uniformly charged insulator. It means it's uniformly charged throughout the interior. Okay? So let's start with the insulator case. So I'm going to start with this case. For this one, we need to define, I guess for the first time, the volumetric charge density, or simply charge density. Charge per volume. This is read as rho. And for this one, we need surface charge density. This one, we need charge density. Right? One is on the surface, another one is throughout the volume. Okay. Can I actually make it bigger? I can. So, the question is, what is the electric field inside this sphere. And what is the electric field outside this sphere? That's the question.
Inside
What?
inside where? Like the center?
Inside at a distance r that is less than big R. So for example, over here. So there will be some electric field pointing in this direction, right? Because of the spherical symmetry, for example, just a brief example, can you calculate if this was a disk of R? Can you calculate anything with Gauss's law? No, because it's finite, it's has funny directing electric fields. No simple surface would do. Okay, so no, very good. But this sphere, although it is finite, it still has so much of a symmetry that you can use Gauss's law. A cube, if you have a cube, can you use Gauss's law? No. Unless we ask you to find flux on one of its sides. Okay?
Is it like we zooming a pointer here?
Very good. Yes, it is like that. It is like that. Or you are, yes, it is like zooming. Oh, it's tiring. 3 hours is tiring, right? Even for me. It's not the tiring, but it's just the weather, like the hot. Yes. Sorry. Please don't hesitate to remind me whenever I forget to give you the attendance sheet. Are the others here? Did I receive the previous ones? They are somewhere here, yes. So, first let's start with R inside. Okay? Let's use Gauss's law. Gauss's law tells you that E times 4 pi r squared has to be Q enclosed over epsilon 0. What is Q enclosed?
Rho times the volume.
Rho times the volume. Everybody agrees with this? Rho times the volume. So,
Inside of this what's
very good. Inside of the Gaussian surface. So 4 pi over 3 r cubed, small r cubed, right? So electric field inside the sphere is going to be rho r over 3 epsilon 0. You see, we have lost pi. So our arguments doesn't go all the way. No, we didn't. It went away with r squared. Okay? Any questions? How about outside? How about outside of the sphere? If you think that the class is over, it's not, because we started 10 minutes late, so we have another 10 minutes. Do you want to leave early? We can stop here if you want, if you can't take it anymore. Yes?
It's just
Sıcak oldu, gidelim mi diyorsunuz? Let's find the electric field outside and go home. Electric field outside is very simple, not zero. E times 4 pi r squared is equal to, what is Q enclosed? Q over epsilon 0. So electric field outside actually is what we know from Coulomb's law. Done. Okay? Everybody's happy? Take good care. Bye bye.